All right, so hopefully you've taken a chance to think about what you think about all of these four statements, whether you think they're true or false. We'll go through them in order. So first, the values for energies or work depend on the choice of observer. So this means whether the observer is moving relative to your system or whether they're at rest. And the answer is that yes, they do. So this is a true statement. Depending on which observer you pick, you could get different energies or works, but the work energy theorem will still be true as long as it's an inertial observer. The second statement, both external and internal forces can do work. This is actually false. Work is the transfer of energy to or from a system. It's positive if energy is transferred in, it's negative if energy is taken out. So we can only have external forces be involved in that transfer. Something that's only internal to the system can't do work and can't transfer energy in or out. The third statement, the total energy of a system is always constant. This is false. You can actually see this from the work energy theorem up here. Delta E system, whenever that's not equal to 0, then the energy is not constant. So we can change the energy of the system by doing work on it. That's what the work energy theorem says. That said, energy is always conserved. That is a true statement. And what that means is more about the type of quantity energy is. So energy is one of these special quantities that's neither created or destroyed in the universe, as far as we can tell. So that means however much energy the universe has today, it will have that same amount of energy tomorrow. It may take on different forms and it may transfer from one system to another, but the total amount of energy is never increased or decreased. We've got the same amount that we're working with. So the correct answer here is E, and hopefully now you can see why. So let's summarize some of these important points that we've talked about already. So yes, the energies depend on our choice of observer or reference frame. So unless you're told otherwise, let's always choose an observer who's at rest with respect to the ground. That'll make sure that they're an inertial observer, and it'll make sure that the energy you calculate is the same as the energy we're calculating. Also, you must specify the system, just like we did with Newton's laws. You've always got to specify the system, in part to determine which forces do work and which are internal to the system and do something else. So a force must be external to do work, like we talked about. And one of the key pieces to figuring out when work is done is to look at the point where the force is applied and to see if that point displaces. Work can only be done if there's a displacement corresponding to the point where the force is applied. And we call that point the force displacement. Or sorry, we call that displacement the force displacement. And then lastly, if you have a conservative force, and this is a special type of force that we'll explore a little bit more why it's special later, but if you have one, then it has the following properties. It turns out that it doesn't matter what path you take between 2 points from your initial state to your final state, the work done is going to be the same no matter which path you would have taken. So if I want to calculate the work done going from here to here, if I have a conservative force, it doesn't matter if I moved along a straight line or if I took like a curly path. As a corollary to that, that means that the work only depends on which 2 endpoints you pick for your initial state and your final state. And if you make those points the same, so if you do a closed path and end where you started, then the work done has to be 0. So for physics 1, the conservative forces that we're going to encounter are the gravitational force is conservative and the ideal spring force is conservative. And it turns out that the fact that those 2 forces are conservative is what makes using the work energy theorem a lot more attractive than Newton's laws in certain cases. So go ahead and keep that in mind. So before we dive into more details to sort of motivate why we're picking this new tool, because, you know, Newton's laws were great, we could do a lot with them. So why are we making things more complicated, especially during the pandemic? Why don't we just stick with what we know? Well, it's because certain problems become really intractable really quickly. So let's just consider a block sliding down a ramp. And let's just even say friction is negligible. We don't have to worry about friction. What is the speed when the block gets to the bottom of the ramp? So you've done something similar to this, but you did it when the ramp was straight. And now what happens when the ramp is curved? Well, let's see if we were going to try to apply Newton's second law to this. We'd say that the net force acting on our system of the block was the mass of the block times its acceleration. And if we know the acceleration at all points in time, then we could integrate the acceleration from the initial time to the final time to figure out what the velocity changed by. And maybe we could figure out then the final speed. But let's look at what the forces on the block actually look like over time. So the weight force points straight down from the center of mass, and the normal force points perpendicular to the ramp, which at the first location shown here is perfectly horizontal. But notice that as the block moves, while the weight force stays the same, the direction of the normal force actually changes. And the magnitude of the normal force will actually change as the block's acceleration changes. Because remember, the normal force, we solve for it with Newton's second law. So it depends on the acceleration, which is the thing we're trying to find. And this problem just keeps happening. As the block moves down the ramp, the normal force keeps changing direction. So there's not like a convenient coordinate system for us to pick to work out this problem. And it just becomes really messy and makes us very sad. But fortunately, the work energy theorem is going to make this problem a lot more tractable, and in part because gravity is a conservative force and we don't even actually have to care about the curvature of the ramp when we do this problem. So that's where things are headed, but we have to build up to that. So let's start looking at the definition of work with this clicker question. So I guess it's not a clicker question anymore because we don't have clickers. But we do want you to, before you open the next video, think about what you would answer this question, and in particular, why. And my recommendation is to think about what the definition of work is in terms of that line integral, and what all of the pieces in that equation, what they really mean. In particular, what is that S initial vector and S final vector? What do those mean? So go ahead and think about that, and then we'll see you in the next video.